Hi everyone, my name is Carrie and I'll be going over question 2 on the Spring 27 midterm 2. So this question is called an operational understanding. So the instructions say, consider the tree on the left where Greek letters represent numerical values. In the boxes to the right, shade all values that might match the text. Assume all values are unique. For BSTs, assume left items are less than. When treating the tree like a graph, assume nothing about the order of adjacency lists. All right, so let's get started. So the first question is asking which of these could be the largest item in a min heap. So we know that a min heap, the root is always the smallest item, and nodes must be smaller than their children. So this alpha value has to be smaller than the beta and pi value. So knowing that all the largest items have to be at the bottom level, so it really could be any one of these, we don't know, but basically they just have to be larger than their parent. So we know it has to be one of these four. So I'm just going to mark these four here. Oops. So now we see the min heap, which is the smallest item. So as I said before, the min heap, the root will always be the smallest item. So this has to be alpha, and it can only be alpha. So for BSTs, how BSTs work is for any node, all items on the left of it are less than, all items on the right of it are greater than. So for this BST, the largest item must thus be the item on the very right. So it's greater than this item and greater than this item, so it has to be this value here. I'll mark that. And similarly, for the BST, the smallest item, it has to be the leftmost item. So it has to be smaller than alpha, smaller than beta, so it has to be this value here. All right, so now let's do the median item of a min heap. So all we really know about a min heap is that the root is the smallest item. So in this in this heap, we know that alpha cannot be the median because it has to be the smallest item. We also know that all the values are unique, so this will definitely be the smallest, and it can't be the median because it's the only one that has that value. So we know that this has to be the smallest, so that means all of these have to be greater than alpha, and there's really, besides that, there aren't really any restrictions on what these values can be. So really, any one of these values can all be the median. And it really just depends on the ordering, because these can really come in any ordering as long as they're greater than alpha, they're totally valid. So basically, just anything besides alpha can be the median item. BSTs though, they're a little bit different. So for this BST, we know that everything on the left of alpha is going to be smaller than it. Everything on the right of alpha is going to be larger than it. So alpha is really just sitting at the middle. So it's got 3 items smaller, 3 items bigger. So therefore, it's the median item. It's the median item out of the 7. All right, so now we have this min heap. What's the new root gonna be after we delete the minimum? So if we delete the minimum, if we delete this value, we still have to have the next smallest value take the root. So the next smallest value is either going to be beta or pi. We don't know which one it could be. It could be either, but it has to be one of these two because we know that these two values must be smaller than these 4 values. So beta or pi, either one would work. And so now let's do BST, new root after Hibbard deletion. So the way Hibbard deletion works is we delete the root and we replace it with its closest item, either smaller or larger. It really depends on the implementation. So we know that its values that are closest to it are either going to be this value or this value, because we know that this value here, this epsilon, it's like in between beta and alpha, and this theta is in between alpha and pi. So either one could be replacing alpha. So it's going to be epsilon or theta. So now min heap, what's the root going to be after we insert some new item? So either the new root will have to be the smallest item. So the smallest item will either be alpha or the new item. So there's really two cases. Either this item here is larger than alpha or it's smaller. If it's larger than alpha, then alpha will still remain the minimum. So that will be the root. So we can mark that here. Or if this new item is smaller than alpha, then this item will become the new root. So that's an option as well. So now we have BST root after inserting new item. So unlike min heaps, we don't really rearrange BSTs when we add stuff in. So really, we could add this item anywhere to where it fits, and we aren't going to change the value of the root. So it's just going to stay at alpha because we don't do any like rearranging or any of that sort of thing. Okay, so for the last question, we'll be doing the last item DQ'd running BFS from omega. So if you remember, BFS is an algorithm for traversing a tree. It starts at a root, explores its neighbors, and then it explores its next level of neighbors, and so on. So we're going to be starting with the root at omega, and then we're going to see how many hops away each item is to see what's the last thing we'll be DQing. So first we're going to see that pi is just one hop away. Oops. And then next we see theta is 2 hops away. Alpha is also 2 hops away. Beta is 3 hops away. Delta is 3, 4 hops away. And then epsilon is also 3, 4 hops away. So you can see here that delta and epsilon are the last values that will be traversed using BFS if we start at omega. So therefore, they will be the last items that will be DQ'd. So now let's move on to part B. So it says, suppose we have an initially empty hash map as discussed in lecture that maps a year to a famous person born that year. Suppose that the hash code of the year is given by the sum of the first and last digits. So for example, the hash code of 1569 would be 10 because 1 plus 9 is 10. So draw the hash table after calling put with the following key value pairs. Assume that each bucket is a list and that there is no resizing. The first one has been completed for you. Assume new items are placed at the end of the list. So I've just gone ahead and I've just kind of created like a little objects that we'll be adding here, and I've also just calculated the hash codes for each item. So we already did this one, but 1 plus 9 is 10, so that hash code is 10, and now we want to see where we put it in the array. So all we do is 10 mod 4, because the array size is 4. That is equal to 2, which is why we put this value in the 2 index. So just a heads up, I'm probably going to butcher a lot of these names, so I apologize in advance. So let's move on to this next one. So we see here that it's 155, so its hash code is 1 plus 5 is 6. So now we want to find out where we put it in the array. So we do 6 mod 4 is also equal to 2. So we can just drag this value also into the 2 index, and we can draw our arrow to connect it. Whoa, that's not an arrow. Whoa, okay, that kind of works. It's a little wobbly, but you get the point. Alright, so now we're going to do this next one. So we have this 1107, so its hash code is 1 plus 7 is 8. We want to find out how it fits in the array, so we mod by 4. That's equal to 0. So we can put this Dandolo item right at index 0 right there. Alright, next we have this value 1737. 1 plus 7 is 8. We mod it by 4 to find out where we can put it in the array. This is 0, so we can drag this item right here and then draw this arrow to indicate that they're connected. Oh. Wow, I'm really bad at drawing arrows. Okay. There we go. So now, let's move on to this one. We have 713, so 7 plus 3 is 10, so that's its hash code. We want to find out where it indexes into the array, so we mod by 4, which is equal to 2. So now we know that this 713 goes into this 2 index. So again, we can just draw this arrow here. Great. So now we have 1048, so its hash code is 1 plus 8 is 9. We want to mod it by 4, so that's equal to 1. So we can put this item at index 1. So last we have 1737. So again, this hash code is 1 plus 7 is 8. We mod by 4, and that's equal to 0. So you would think that we would just add a new item, 1737 Hancock, to index 0, but we see that this 1737 key already exists in this 0 index. So it already has, this 1737 is a key that already exists. So what we're going to do is when we put in Hancock, we're going to replace this Payne value with Hancock instead. So Hancock, because it has the same key as Payne, it overrides its value. And that is our final hash map. Hope that helped.